All right, guys, welcome to your Unit 7 test study guide. Let's go ahead and get started here with part 1. So let's go ahead and start off by reading the introduction here. We have a squirrel starting at building A at time t equals 0, traveling along a straight and horizontal wire connected to another building, building B, and we're looking at an 18-second time interval here. I said seconds, I don't really know what the units of time are, but 18 units of time. The squirrel's velocity is modeled by this piecewise linear function, so this graph represents the velocity of the squirrel, right? So number 1 is our first question. Let's begin. On what interval is the squirrel moving toward the right? So I'm going to be writing my answer up here. The squirrel is moving to the right when velocity is greater than 0. Okay, so recall that velocity tells you what direction you're moving. A positive velocity either means you're moving to the right when you're on a horizontal axis, which we are in this case, or it could mean you're moving up if you're on a vertical axis. So anytime velocity is greater than 0. Now that's going to happen at any time when this graph is above the x-axis, because up here my velocity, represented by the line, is positive because it's above the x-axis. So, and we also have it over here. So there's actually going to be 2 intervals where the velocity is greater than 0. And this occurs on 0 to 9 and 15 to 18. And that's the answer, number 1. Let's go ahead and take a look at number 2. Okay, on what interval is the squirrel speeding up? Explain your answer. So as we've mentioned a few times in this unit, a moving object, or I guess in this case animal, is speeding up anytime its acceleration and its velocity are either both positive or both negative. In other words, they have the same sign. Now we've already mentioned that velocity is positive anytime this line is above the x-axis. So it's on these intervals that my velocity is positive. And therefore it's not too difficult to see then that on this interval down here, my velocity would be negative. Now, hopefully at this time you guys realize that acceleration is the derivative of velocity. In other words, acceleration is going to be the slope of this velocity graph. Derivative is just a fancy word for slope, right? So if acceleration is the derivative of velocity, that means that acceleration is the slope of this graph. And so we're going to have a positive acceleration anytime there's a positive slope. And so we would have a positive slope anywhere where the line is going in an upward direction. So that would be a positive slope, and this would be a positive slope. So we have 2 places where we have a positive slope. And we will have a negative acceleration anytime there is a negative slope. So that would be like from here to here. Okay. Now, as we said, the squirrel is going to be speeding up anytime the velocity and acceleration are the same sign. So a positive velocity put together with a positive acceleration is one instance where you would have the squirrel speeding up. And another instance where you would have the squirrel speeding up is if you had a negative velocity with a negative acceleration. So I like doing the color coordinating thing here. It's helpful. So now we can see that the squirrel's going to be speeding up anytime there's blue and green put together. And so right here, the squirrel is speeding up. And also right here, the squirrel is speeding up. I don't see any other places where there's a blue and a green, though. Now, another place where the squirrel is speeding up is anytime we have a negative velocity and negative acceleration. So that would be anywhere where we have a pink and an orange. And so there's only one place where that happens, and it's right here. So there are 3 intervals where the squirrel is speeding up. And in your explanations for this is all this work that I just did with these colors and this chart over here, if you want to call it a chart. That stuff is not necessary. I'm just doing that for teaching so that you guys understand what I'm looking at. But your explanation should include what I wrote here, and then the intervals where that happens. So you could say now, this occurs, let me go back to doing a red color here. This occurs on the following three intervals, 0 to 2, 9 to 10, and 15 to 16. So what I've got written in red up here is really all that you need to have for your answer. All this other stuff I was doing was just to help you understand my thinking. All right, so that's the end of number 2. Move on to number 3. Okay, so for number 3, it says find and interpret this expression here. So let's go ahead and find it first. We're integrating velocity. Now this is a velocity graph. And when you do an integral of a graph, that's basically the area under the curve. So I want to find the area under the curve from 0 up to 14. So I actually want to stop right here. So I only want to be finding the area from here and up to here. The rest of it I really don't want. So we only want to find the area of these two trapezoids. Now, there's a couple ways you guys can go about finding the areas of these curves or these sections. Be creative, be quick about it. I think the fastest way would be to do trapezoid. So I'm going to go with that, but some of you guys might have broken it up into rectangles and triangles, and that's fine too. If you're going with trapezoids, though, you do base 1 plus base 2. So base 1 is 9. Well, it's actually what I just called base 2. Base 2 is 9. And base 1, I'm going from 2 to 7, so that's a length of 5. And you multiply that by the height cut in half. So the height is 20, cut in half is 10. So that's going to be my first trapezoid. And then the other trapezoid has a base of from 9 to 14 is 5. And then another base of 10 to 14, which is 4. And a height of negative 10 cut in half is 5. Now, you can keep it as negative, though, because this is an area under the curve. So this area here is going to end up being 140 for the positive one. And for this other one here, that's going to be 45, but it's a negative 45 because that one is under the x-axis. You want to keep that sort of stuff in mind. All right, and so we can go ahead and just combine those together, and we'll see what we get here. I believe 95 would be that. And well, what is that though? So that's the answer. So we've found it, but now we need to interpret it. Well, hopefully we understand at this point that this represents displacement. So what this represents is that this displacement of the squirrel from t equals 0 to t equals 14 is 95. Now that's one way you can interpret it, but I like to make sure that you guys actually know what displacement means as well. So there's a better interpretation, in my opinion. The better interpretation is where you kind of, instead of using the word displacement, you actually just kind of explain that in your answer. So displacement tells you how far the squirrel is away from where he started. This is a positive 95. And so that means that the squirrel is 95 units away from, or actually we should say to the right of, his starting point. And I like this one the best, because this one really includes more of the context of the story problem in it. This is more of like just a straight up raw math answer here. But I like this one because not only does it answer the question well, but it also interprets it in light of the story. So the squirrel is 95 units away from his starting point, which is building A at that time. And so basically what happened is at this point in time, the squirrel's at building A, and since this is a positive displacement here, that's how far the squirrel ran away from building A until he got to 9. But after he got to t equals 9, Then he started running back towards building A because this is a negative displacement. So he ran 140 feet away from building A, and then he ran 45 feet back towards building A, which means that where he stopped was a total of 95 units to the right of building A. I like that interpretation. But I'll accept both. Right, our next one looks very similar. It's just a little bit different here. But we want to find and interpret what this means in the context of our story. Well, when you take an integral of an absolute value, mathematically what happens is we're still going to have those same trapezoids, right? It's going to be 140 and negative 45, which we found in the last problem. This trapezoid was 140 units. This one was negative 45. But the difference is when you're taking the absolute value, we don't care about the direction that the squirrel went. We just care about the distance that the squirrel went. And so that means we have 140 plus 45 now, which means that, yes, the squirrel ran a total of, just a moment, let me back up here, 45. Squirrel ran 140 feet away from building A, but then ran 45 feet back towards building A. But that's a total distance of 185 units. Okay, so our interpretation of this would be that the squirrel ran a total distance of 185 units. And we should include our time unit there. Which, by the way, I think I might have forgot to do that on the interpretation that I liked better on the last problem. I think I might have forgot to put the time in there. And that should be there. That's part of our interpretation. So when you have absolute value, you make everything positive and add together. And what it represents is the distance that the squirrel ran. So we could even put that in there. Ran a total distance of, just to be, I would accept this as an answer, but might as well put the word in there, distance, because that's kind of the key word we're looking for. So I'm going to include it. All right, let's go ahead and move on to number 5. Write an integral function, s of x, that gives the position of the squirrel at time x. All right. So the squirrel's final position is given by taking the squirrel's starting position, which he starts at time 0, plus the integral from that starting time to some variable ending time. And we're integrating the velocity function, which gives us our displacement. So starting position plus displacement equals final position. Now we could be a little bit more specific here though, because we actually know what S of 0 is. It tells us that the squirrel starts at building A. And so all these lengths here represent how far away from building A the squirrel is. So at the beginning, since he's right at the building's location, his starting position is 0. And whenever your starting position is 0, you actually don't even have to include that in the answer. But I'm going to include it just so you guys know that you do want to have a starting position there usually. Okay, but there's our answer to number 5. Right, our next question is, when is the squirrel farthest away from building A? When is the squirrel farthest away from building A? Well, anytime they're asking about something being farthest or greatest or something like that, the question is all about a max or a min. And unless they say relative, you can assume they're talking about an absolute max or a min. We're looking for an absolute min or an absolute max. And when you're looking for an absolute min or an absolute max, you're going to do the candidates test. So my input variable is time, and my output variable is when he's farthest away from building A, well, that's the function that we just created. It was function S. I'm going to put, I guess I'll put X here. Kind of confusing because my input variable is T. I think I'll go ahead and change it just to X for now, because the integral function made things kind of funky there. All right. Anyway, and as you guys know, when you do the candidates test, your starting time is 0, and you also put in your ending time, which is 18. So you always start with your starting point, starting time, and ending time. The next thing you're going to do is you're going to look for the critical values of this function. Critical values are those places where the relative extrema could be located. And relative extrema, like the endpoint, are other candidates. So we want to find the critical values of S of x. Now, to find critical values, you need to find S prime. Now, we just got through saying what our S function was on question number 5. Our S function looked like this. So if we wanted to find the derivative of that, the 0 is just going to go away because it's a constant. And when you take the derivative of an integral function, and that integral function just has a number down here and a variable up here, the integral goes away, and the variable drops inside, and all you're left with is that function now with that variable inside. So my derivative is basically, my derivative of the position of the squirrel is just velocity, but we kind of already knew that anyway, didn't we? We learned that back in chapter 4, that the derivative of position is velocity. So that ties in nicely with what we've been learning. But anyway, critical values are those places where the derivative equals 0. So I'm going to plug 0 in for S prime because that's when the derivative equals 0. And so when the derivative equals 0, that means that the velocity equals 0. And when does velocity equal 0? Well, since this is my velocity graph, velocity equals 0 anytime it touches the x-axis. So these two values of time right here are the places, are the values of x that will make velocity equal to 0. And so we have 9 seconds, and we also have 15 seconds as critical values. Now the next thing we want to do is we want to find what is the squirrel's position at each one of those times. What was his position at the beginning? What was his position at each one of these critical values? And what was his position at the end? One of those has to be the greatest distance from building A, and the other one would have to be the least distant from building A, because we know the extreme value theorem. So, well, we already answered this. S of 0 is 0. The squirrel starts at building A, so his distance from building A is 0. Let's go ahead and see if we can find these other values here. So if I wanted to find S of 9, then I need to take my position function here and plug 9 in for the x. All right, so this piece here, we're looking for the area under the curve of V from 0 to 9. And we did that earlier. That was 140. Plus 0 equals S of 9. And therefore S of 9 equals 140. And we have that answer. All right, next we want to find S of 15. And so we're going to plug in 15 now into our position function. And so basically I just want to find the area under the curve from 0 to 15 and add 0 to it. So as we've already said, this was 140. And we also figured out earlier that, well, actually we haven't figured out this whole thing yet. Last time we stopped at 14. So to figure out the area of this trapezoid, we want to do our base, which is from 9 to 15. That's a base of what, 6? And then this base from 10 to 4 is 4. And then we have a height of negative 10 here, so half of that's going to be 5. So that's going to be 15. That's going to be 10 times 5 is 50. And it's below the x-axis, so it's negative. And so the area under the curve or in this case, we call that the displacement, is 140 minus 50, which is 90. And so the squirrel's position at s equals 15 is 90. And then we have one more problem to do. We got to find s of 18 doing the same thing. So we're going to go ahead and plug in 18. We know this is 140. We know this is negative 50. And we want to go all the way up to 18 now. So I need this last trapezoid. It has a base up top here of 2, a base down here of 3. 3 plus 2 is 5 times half the height, which is going to be 5. And so this trapezoid has an area of 25. If I just add these up, we already know that these two make 90. So if you add 25 to it, you get 115. And there it is. So now the question is, when is the squirrel farthest away from building A? Well, S of x represents his distance from building A. And it's at this point where the squirrel's distance is greatest from building A. The question is asking us about when, so that's a time question. So the answer to our question here is not 140. The answer to our question is t equals 9. Now, if they asked what was the squirrel's greatest distance from building A, then you could say 140. But in this case, they're asking when was the squirrel farthest away from building A, and that answer is 9. All right, so part 2. A water tank at Camp Newton holds 1,200 gallons of water at t equals 0. And on the time interval from 0 to 18 hours, water is pumped into the tank at this rate. So this is how fast water is coming into the tank in gallons per hour at any given time t. During the same time interval, water is being removed from the tank at this rate. And once again, that's gallons per hour. So our first task here is going to be to write a function t of x that gives the total amount of water in the tank at any given time. So when you have a rate in and rate out question, it's a lot like what we did on part 1 with a slight little difference. Your final amount, which we're going to call t, the problem tells us to do that, is equal to the starting amount, which once again, we're starting at time equals 0, but be careful, it doesn't always start at time equals 0, plus the integral of your starting time, which is 0, up to your final time, which we're going to call whatever this variable is here, x. And this is where it's different from part 1. Part 1 just had one function here. It was just the velocity. But on part 2, we're doing a rate in and rate out. So we actually have two velocities working against each other. We have the rate in function, which comes first, minus the rate out function, which comes second. But it still tells us, ultimately in the end, the same thing. The final amount of water in the tank is equal to the starting amount plus the net change in the amount of water in the tank at any given time. And so that's the answer to number 7. Okay, let's move on to number 8. How much water was in the tank at t equals 18? So to answer that question, we're going to take our answer from part 1, which was the function, and we're going to plug 18 in for the time value that they're asking about. All right. Now, we already know what t of 0 is. That's the starting amount of water in the tank. So we know that that one is 1,200. So what we need to do then is we need to type this into our calculator, but not before we've told our calculator what W and R are in the first place. So let's go to our trusty calculators. Now I've already typed them in. If you're having issues getting the right answer, you might want to compare to how you typed your functions in to how I typed my functions in. Okay, just to make sure that we match. All right, so now we want to go to second and we want to go to quit or mode, and then that takes us back to the home screen. where we're going to enter that equation we just had. So that was 1200 plus the integral is math 9. And we're going from 0, in this case we're going up to 18. And we do our rate in W, which I stored under Y1. So I'm going to go to vars, Y vars 1, 1, minus my rate out function, which I stored under Y2. I'm going to put our dx there, and then we push enter, and we'll have our answer. So it's 1309.788, and we're always going to round to the thousandths place. Okay, so our final answer would be 1309.788, and that's going to be in gallons. Now, how do I know the units are gallons? Well, you can tell by the question, but also from the math. I mean, this 1200, that's a gallon, right? And then here, W and R, those are gallons per hour. And we talked about how when you integrate gallons per hour, it cancels a time unit off the bottom, so you're just left with gallons. So you have gallon plus gallon equals gallons. So it's 1309.788 gallons at the end of that 18-hour period. All right, move on to number 9. Number 9 says, find and interpret t prime of 18. So the first thing we're going to do is we're going to take our position function, which we found in number 1, and we're going to find its derivative. Now, when you take the derivative of these position functions, the constant part just goes away, because when you take the derivative of a constant that's being added, it just becomes 0, so we can get rid of it, so to speak. And then when you take the derivative of the integral, so long as there's just a number down here and just a variable here, we can apply the second fundamental theorem of calculus, which says you drop the integral, and then you put the x in the place of the t's there. So the derivative then of t would just be w of x minus r of x. Now they're asking us to find t prime of 18. So after you find your derivative, you're going to go ahead and plug 18 in. And after that, it's pretty much a calculator problem. On my calculator, I've stored w as y1, and I've stored r as y2. So I just need to type this into my calculator, and we will have our answer. So we have y1, which is w of 18, minus y2, which is r of 18. And we're going to push enter, and we get negative 13.443. And so now we're going to interpret things here, right? We need to interpret the number we plugged in. Well, that's an hour value. So this is 18 hours that have gone by. And then we need to interpret this number here, which comes from W and R being subtracted. Now, both W and R are in gallons per hour, and so therefore this answer is in gallons per hour. And so what this is telling us is this is a rate of change, and it's negative. So therefore, it's a decreasing value. But what's decreasing? It's the top value, the gallons. So what's happening is we are losing 13.443 gallons every hour at the time value 18 hours. So here's how we'll write that. At t equals 18 hours, the amount of water in the tank is decreasing at a rate of 13.443 gallons per hour. And that is number 9. Let's move on to number 10. Okay, so on what time interval is the amount of water in the tank increasing? We just saw a point in time when it's decreasing, but I want to know what intervals is this water in the tank increasing. Well, you're going to take your t function. I want to know when this function is increasing or decreasing. Now I know that this function is increasing or decreasing based on the derivative. If the derivative is greater than 0, well, that would mean that t is increasing. In other words, the amount of the number of gallons in the tank is increasing if the derivative is greater than 0. But if the derivative is less than 0, that means that the number of gallons in the tank, represented by t, would be decreasing. So we want to know when is it increasing. So basically, I want to find when does t prime of 0 greater than 10 prime of x greater than 0. because that's when t is increasing. All right, fair enough. So how do we do this then? Well, we already know something, don't we? From an earlier question. We know that t prime is equal to w of x minus r of x. So t prime is greater than 0 anytime w of x minus r of x is greater than 0. Now, if we just add the r of x to the other side, we get this. Now, this actually just makes a ton of sense if you think about it. I want to know, when is the rate of change of the amount of water in the tank increasing? Well, that would be anytime the rate in is greater than the rate out. Now, how can you tell that by looking at a graph? Well, you can tell that anytime w is higher than r of x on the graph. So let's go ahead and take a look at the graph of w of x and r of x at the same time, and we're going to find those places where w of x is higher than r of x. Now, depending on what kind of functions you've been doing lately, it's kind of hard to say what your window will look like when you graph yours, but you should be able to just push graph and you should see something. Now, I know that the x-axis is usually easy to set because we know that we want to be going from 0 to 18. So let's go to our window here, and we're going to set our minimum x value at 0, and we're going to set our maximum x value at 18. I'll graph it again here. But as you guys can see, we don't need to see anything down here. But I do need to see a little bit more about what's going on up here. So I need to see a higher y value, but I don't need to see any negative y values. So now I'm going to go back to my window, and I'm going to go down to the y's. I don't need to see anything less than 0 for the y values. But my y max, I'm going to go ahead and say, let's go ahead and jump it on up to 50 and see if that's high enough. Still kind of going off the chart there. So I'm going to go even higher now. Let's go on up to like maybe 100. Let's try 100 for my y value. Ugh, still off the charts. All right, I'm going to try 200. So you just got to kind of play with it sometimes until you can see enough of it. Getting closer. We're almost to the top of those peaks. Let's try one more time. Let's go on all the way to 300. There we go. All right, now we can see where the height of these graphs ends. Now, remember, we were looking for the places where w of x, I'm going to write this down so we can remember it, where w, which I have encoded as y1, is greater than r, which I have encoded on my calculator as y2. Now, you can't tell right now which one is which, right? But there's a way you can know it. You're going to push this button up here that says trace. Let me clear my history here so you can see the buttons I'm pushing. You're going to push the button here that says trace. And as you can see, my cursor is on this blue line here. And if you look at the top, that's y1. So the blue line is y1, or my rate in. And the red line is my rate out. Let's go ahead and label those with some color coding right now, so it's easy to remember those. Now, as we said before, we're looking for those places where the rate in is greater than the rate out. So in other words, I want to know where are those places where the blue line is above the red line. Well, pretty easy to see here just by looking. The blue line is higher than the red line on this interval right here. So what we need to do is we need to figure out what are these x values right here and here where they're crossing, because that's the interval that I need to have. So we need to know how to find where those lines are crossing, which we've done before. So let's go ahead and we'll do that really quick. How do you find where two lines are crossing? Well, you're going to push second Let me clear my history actually before we get started. You're going to push second, and then you're going to push trace or calc, and then you're going to click 5 for intersect, and then you're just going to scroll until you get to where those lines are crossing, and then you're going to push enter 3 times. And there's my first place where those lines are crossing. Now, I want to store this number. You could just write it down, but I like to store it because every time you write it down, you have to round it. But if you store it on your calculator doesn't round it and it keeps it exact. So how do you store it? Well, when you're in graphing mode, first of all, you have to push enter. And then after that, you push store. I think I lost it actually. Let me try that again. And after you, so I got it to work. I'm not sure what happened there, but anyway, you push enter and then you push store and it takes you back to the home screen, and you're just going to put a variable there. So we're going to push alpha A and enter, and it should store that value for you now under A. We go back to our graph and we're going to find the other place where they intersect. So once again, second calc, 5, scroll, and enter 3 times. And there's my second value. So to store that, we're going to push enter again. Then we push store, and we're going to put that as B. All right. So I don't know why I stored them. I guess I really didn't need to do that. I just need to know where they're crossing. So these are my intervals, though. So the answer to our question then will be on the interval from 6.495, we're going to round that number up now, to 12.975. So that's the interval where the W function is higher than the R function. And when the W function is higher than the R function, that's whenever the rate in is greater than the rate out, which means that the overall rate of change is increasing and positive, and that's the answer to our question. All right, so let's go ahead and move on to number 11. All right. So what is the maximum amount of water in the tank on the interval from 0 to 18? Okay, so once again, they're asking for a maximum amount of water. We have a function for the amount of water. It's the t function that we found earlier in this problem. And when you're looking for a maximum, unless they say relative, you can assume they're looking for an absolute maximum, which means we're going to do the candidates test. And once again, you always put your starting time in there and your ending time, as well as the critical values. The critical values are those places where the derivative equals 0. We've already seen from an earlier question that the derivative of t is w of x minus r of x. And if w of x minus r of x equals 0, well, then that means that w of x equals r of x, just because you can add r of x to both sides, right? So we're looking for those places where the w function and the r function intersect. Now, we already found some of those on an earlier question. I've stored one of them as 6.495, and I've stored the other one as 12.975. Now, let's go back to our graph. There might be some more, though. It's possible they're intersecting over here at 0, but I don't think we really need to worry about it. And 18 stops here, and they don't get to touch again. So actually, we've already found it. But if you don't want to go back and watch again how you find where they cross, I'll show you how you find where these two lines cross. You're going to push second. Let me clear my history, actually, so you guys can follow the button. I'm pushing a little bit more easily here. So you're going to push second, trace 5. You're going to scroll over until you get to a place where the blue line and the red line here are intersecting, and you push enter 3 times, and it tells you the answer. And then if you want to store it, you push enter. And then you push store, and then alpha, and then pick a letter. So there we have it. So I've already got my two places where they cross, which I'm calling A and B. So since A and B are the places where W of x and R of x intersect, that's the place where W of x and R of x are equal. And since W of x and R of x are equal, that would mean that at those points, this equals 0, and therefore the derivative equals 0, and those would be my values. Now, on your FRQ, you cannot just put A and B here. You do need to define them. But the benefit to defining them once is that from now on, anytime you need to use those numbers, you can just put A and B so long as you define them at least once. But if you don't at least define them once, then your AP graders will be wondering, well, what do they mean by A? But if you define it, they won't have to wonder. All right, so now we need to find T of 0, T of A, T of B, and T of 18. Now, I'm pretty sure we already found T of 18 in an earlier question. I believe it was like 1309 point something. I think it was the answer to question number, or the second question to part 2. You can go back and take a look at that. T of 0 is the starting amount. That's 1200. And you guys will find a lot of times on AP exams that they will ask these types of questions in such a way that the answers to some of these you've already done because they want to save you some time. Believe it or not, sometimes they're nice. But anyway, we still need to do T of A and T of B. So we're going to take our position function, which we found way back in question, the very first question on part 2 here. And we're going to plug into that position function the A value, which goes here and here. And then we're going to do the same thing with the B. But all that's going to take place on our calculator. So let's do it on our calculator. So I've got 1200 plus the integral from 0 to A of y1 minus y2. And I get 525.242. Now we want to do T of B. So we're just going to go back to our calculator at this point. And instead of retyping this whole thing, the only change I need to do is change this A into a B. So I'm just going to do second entry to bring back my last entry there. I'm going to scroll back until I get to the A. I'm going to delete that. And then in its place, I'm going to put alpha B. And then all I have to do is push enter. Another time-saving strategy. So now we're up to 1697.441. And so now we've found our values at all of our candidates, beginning, ending, and criticals. And these are the outputs. And all these are gallons. So when did we have the maximum amount of water? Or actually, it's not asking when. It's asking what is the maximum amount of water. And so we don't want the time value. We want the water value. And so the answer is 1,697.441 gallons of water. All right, number 12. How much water was drained from the tank on the interval from 0 to 18? So now this question is asking us about how much water was drained, which means that on this problem, I really don't care about water coming in. I really only care about water going out. Now, this is a rate. This is how fast water is leaving the tank. But they're asking how much water drained from the tank. Well, I can turn gallons per hour into gallons by integrating. And so that's how we're going to answer this question. If you want to find out how much water on the interval from 0 to 18 was lost, you're going to take the rate at which it's leaving the tank, and you're going to integrate that with respect to t over the time period they're asking about. And that will tell you the total amount of water that was drained from the tank. So let's go ahead and go to our calculator and let it do the work for us. Math, 9, 0 to 18, with the rate out function r, which I've stored under y2. and that would be 2,585.668 gallons. And there you guys have it. So that's the answer to number 12. Let's move on to number 13. All right, so let's go ahead and take a look at this one. W of 10. Well, that's actually pretty simple. We're just going to plug 10 into this function up here. But they want us to interpret what it means. So let's go ahead and plug it in first. So W of 10, I've stored W as Y1 on my calculator. I'm just going to plug 10 into that. And I get 297.663. But we do want to interpret this. Now this number here is a time, so that's 10 hours. So at the 10th hour, what is this? Well, that's W, and W is measured in gallons per hour, and that's the rate at which water is being pumped into the tank. So at the 10th hour, 297.663 gallons per hour are coming into the tank. Okay, so how would I write that as my answer? At t equals 10 hours, water is coming into the tank at a rate of 297.663 gallons per hour. Moving on to number 14. All right, so this one says find and interpret W prime of 10. Okay, well, we can just do that on our calculator again. It's been a while since we've done derivatives on our calculator, but we can do that. Let me show you how to do that really quick. The way you do a derivative is you're going to push math, and you're going to select 8 for derivative. We're going to put x here to indicate we're finding the derivative with respect to x. And I'm going to put my w function in here, which I've stored under y1. So I'm going to go to y bars, select y1. And I want to find the derivative at x equals 10. And that's how you find the derivative. And it's 5.342. So that part's not too bad, but now we got to interpret it, and that's where things get a little interesting. This is hours, of course. We've mentioned that already before in a previous problem. What is this, though? We know that W is gallons per hour. It's a rate. So what happens when you take the derivative of a rate? Well, that's kind of like taking the derivative of a derivative. And the derivative of a derivative is going to be gallons per hour squared. Every time you take a derivative, you get an extra time factor on the bottom. It's like the opposite of integrals. When you integrate, you lose a time factor on the bottom. But when you find a derivative, you get a time factor on the bottom. So this is going to be 5.432 gallons per hour squared. Okay, so how would we interpret this? So at t equals 10 hours, the rate at which water is filling the tank, now that's just English for W, because that's what W is. W is the rate at which water is filling the tank. At t equals 10 hours, W, the rate at which water is filling the tank, is itself increasing because the rate of change of W is positive, and it's increasing at a rate of 5.432 gallons per hour, or you could say per hour squared, or you could say per hour every hour. There's a few different ways you could say it. But basically what this means is that, usually, water's pouring into the tank at a certain number of gallons per hour, but that water is coming in at a faster and faster rate. And so this is telling us how fast the rate itself is increasing. So the rate itself is increasing by 5.432 gallons per hour every hour at that exact point in time of t equals 10. All right, next question. So this is a challenge question. I don't think I'm going to go over time. I'm not going to take time to go over this, but you guys can ponder it. Maybe it'll show up on the test as an extra credit question or something like that. I don't know. We'll see. Maybe, maybe not. No promises. But at what time was water draining from the tank at its fastest rate? Well, that sure sounds like a max-min candidates test type question. But what would we be finding the min or max of? Interesting. I don't know. I'll let you guys think about it. All right, let's move on to part 3. A particle moves along the x-axis so that its velocity from t equals 0 to 5 is given by this function here, and the particle's position at x equals 8 is t equals 0. So our first question is, what distance did the particle travel on the interval from 0 to 5? Well, we have a formula for distance, don't we? The formula for distance is the integral of the absolute value of velocity. And the interval we're looking at here is from 0 to 5. So that's just going to be a calculator question. Let's go ahead and turn to our calculators. Of course, the first thing we're going to do is we're going to put the equation in under y1. We're going to go back to the home screen here. We're going to do math. 9. We're going from 0 to 5. You want the absolute value in there, so you push math. Scroll over to num. Press 1 for absolute value. Put your function in there, which we've stored under y1. And don't forget your and we should have our distance there, 5.112. And that will be our answer. Move on to the next question. All right, question number 17. Write a function that gives the position of this particle at time x. Well, the position function of a moving particle can be found by taking its starting position, and it's starting at t equals 0, and adding that to its displacement from that starting time to the ending time of interest, which in this case is t, where we integrate the velocity on that time interval, thus giving us the displacement. So displacement plus starting position equals final position. And now we also happen to know that the starting position of this particle is 8, because the directions tell us that. And I think I'm going to go ahead and change something here. I'm going to just change this to, I think I'll change the S here to an X, I think is what I'll do. I apologize about changing that. I just noticed an inconsistency. Up here I was calling it X, but over here I was calling it X. So I'm just going to call it X. But anyway, so there's that. That's my position function. So that's pretty much the end of question number 17. Move on to our next one. All right. At what time did the particle reach its farthest point to the left? So we've got another candidates test question here, because anytime you're being asked to find the furthest or the greatest, you are being asked to do an absolute max or min, which is candidates test. My input variable is t, my output variable is x, and we always start with our greatest and least time values from 0 and 5. And then we want to find those places where the critical values are. Critical values are those places where you could have relative extrema, and relative extrema are also places where the absolute max and min could be located. So critical values are those places where the derivative of the function you're looking at equals 0. So the function I'm looking at, as we've already said in a previous question, is 8 plus the integral from that function. And I want to find the critical values of this function, which can be found by taking the derivative of it. When you take the derivative of that function, the 8's going to go away because it's a constant number that's being added. And when you take the derivative of this piece, since it has a number down here and just a variable here, we can apply the second fundamental theorem of calculus, which says we're allowed to just drop that off and slip that t in there, which it's already in there, and gives us this. And that makes sense because we learned in an earlier chapter of this year that the derivative of position is velocity anyway, so that makes sense. All right, now we want to find where does that where does that derivative equal 0? Well, that's where the velocity equals 0. Now, how are we going to do that? Sometimes it's possible to just take your velocity and plug it in here and then just do it by hand. However, this time we have a little bit more of a complicated equation, and trying to solve that is not going to be so friendly. Another way we could do it is with our calculator once again. You can find where a function equals 0 by looking at the graph and seeing where the graph touches the x-axis, which is how we're going to go ahead and do this problem. So here's my graph, and I can see that it's touching the x-axis in 2 spots. One's here and one's here. Now, by the way, we only really care about a certain interval. Now, you don't have to change your window, but I'm going to be picky about it, and I'm going to change my window. We only want to see from x equals 0 to x equals 5. There. And also, this looks pretty flat. We don't need quite this much height or this much down here. Now, you don't have to change it if you don't want to, once again, but I'm gonna reduce this. I don't need to go all the way down to -10 on the y-axis. I think we can probably settle with like maybe -5, and for the maximum y value, I think we can go like 5. And that we can kind of get a little bit more clear of a graph here. But anyway, I want to find those places where it's touching the x-axis, because where this velocity function is touching the x-axis, that's where the derivative of x is equal to 0. So how do we find where it touches the x-axis? We're going to do the following key sequence. We're going to push second, calc and trace. You're going to choose option 2 for 0. And what you're going to do is you're going to scroll your cursor until it's to the left of the intersection point that you want. So let's say I want to find this root right here. What I'm going to do is I'm going to scroll my cursor until it is to the left of that root. So just to the left of it. And once it's to the left of it, we're going to push enter, and that puts a marker there. And now we're going to scroll to the right of it, and then we're going to put another enter in there for another marker. And now our calculator knows to look between these two arrows here for a root. And so we push enter one more time, and it tells us, oh, it's 1. Nice. Okay. Wonder if we could have told just by looking. I wonder if the next one's 2. Probably is. Let's see. You don't want to guess. It could be off. What if it's like 2.9? Probably isn't, but let's check just in case. So we do second, calc 2, scroll to the left, enter, scroll to the right, enter, and enter one more time. And yep, sure enough, it's 2. All right. So go ahead and go back and do some more now. Now, in this problem, we got a little bit lucky, and we got some pretty nice numbers, 1 and 2. So those are easy to put here in our table. But don't forget, if you get a weird, funky, big, long decimal number, just store it on your calculator as A, and just put A equals and round your answer here. And then from there on out, just use A to reference that number. Because otherwise, it's just a pain in the butt to keep writing it. And it's also less accurate. Now we want to find x of 0. We want to find x of 1. We want to find 2. And we want to find x of 5. All right, now x of 0 is easy because we're just given that up here. X equals 8 at 0, so that answers 8. Let's do 1 as our next one. So if you want to find out where what x of 1 is, what you're going to do is we're going to come back to our position function, which we had up here initially. Let me get rid of some stuff here that we don't need anymore. Want to come up here to your position function, and you're going to want to plug in 1 for t. And we're just going to let our calculator do it. When we're all done doing that, we're going to let our calculator also do the same thing for 2 and 5. So let's go ahead and transition to our calculator now and let the calculator do more of the work for us. So we want to get to our home screen, so let's push second and quit. And we're going to do our 8 plus the integral from 0 to 1 was the first one we're going to do. We're going to put our velocity function in there, which we've stored under y1. Yes. So that gives me 8.554. Now, we also wanted to enter 2 and 5. So instead of retyping it, though, I just need to push second and enter, and it brings back the whole equation for me. And I just need to scroll back and replace the 1 with a 2. Enter, and then bring back the equation again. Scroll back and replace that 2 with a 5. And now we have all the values that we wanted. We have 8.554, 8.368, and 12.739. And the question is, when is this object farthest to the left? Well, that must be at the very beginning, because all these other numbers are too big. All right. Question 19. Last one for part 3. On what interval or intervals was the particle slowing down? Well, we know that a particle is slowing down when its velocity and its acceleration are opposite signs. When its velocity and its acceleration are opposite signs. All right, well, first of all, we need to understand that acceleration is equal to the derivative of velocity. Now, there's 2 ways we could handle this problem. Okay, one way is by letting the calculator do the work for us. The other way is by doing it by hand. And I'm going to do it both ways. I'm going to start off by doing it by hand, and then after that, I'm going to show you guys how to do it on the calculator, and you could choose whichever method you prefer. Now, the derivative isn't too bad to do by hand, actually. You would have to do a chain rule to this thing. First of all, when you take the derivative of an ln, it's always going to be 1 over whatever's inside of the ln. It's been a while, huh? You guys are like, oh my gosh, I forgot about that stuff. All right, and then you multiply it by the derivative of the inside, which is 2t minus 3. Now, if you put these things together, which we probably should, so it looks a little bit cleaner, it would be just putting the 2t3 on top. And then what we could do is we could go ahead and graph that as well as our velocity function. So I'm going to go to my y equals page. I'm going to put a new function. I'm going to put the acceleration function in there, which is the derivative of the one that we already have. That's 2x minus 3. Matter of fact, I think I'm going to put that in parentheses. When you do a fraction, if there's more than one term, usually it's a good idea to put the numerator and denominator in parentheses. And that's my acceleration function. And then we can graph it. Now, let's take a look at our velocity function first. Now, our velocity function is this blue line. And the blue line, well, my velocity is going to be positive anytime the blue line is above the x-axis. So from here to here, I've got a positive velocity. And also from here to here, I've got a positive velocity. And we can also see that we have a negative velocity then from here to here because it's below the x-axis. Now the red line is my acceleration function. And in the same way, the acceleration is going to be negative anytime it's below the x-axis. And it's going to be positive anytime it's above the x-axis. Now something that might help us out here is we're also going to want to know where is that acceleration function touching the x-axis, which we have learned before how to do. So what you're going to do, if you forgot, is you're going to push second, Calc, 5 is intersect, and you're going to scroll your cursor until you get to that place where, actually I take that back. I'm saying that all wrong. Let's back up for a second. That's not how you do this. What you're going to do is you're going to push second, Calc, and you're going to select 0, option 2. And you also notice I'm on the wrong line right now. I'm on this blue line. So if you ever want to switch from one function to the other, just push up or down, and it takes you to the other function. Now we're going to scroll to where it's touching the x-axis, and we want to pick a number to the left of that intersection point. And then we're going to pick a number to the right of that intersection point. And then enter again, it will tell us there. So it's 1.5 is where that one's touching. Okay. Now I'm going to go ahead and just make a number line test. So I'm going to do a line for velocity, and then I'm going to do a line for acceleration. Now my velocity touches the x-axis at 1 and 2, which we found earlier. So I'm going to put the numbers 1 on here and 2. And my acceleration function is touching the x-axis at 1.5. Now, that breaks up this number line here into a couple of different regions. Okay. Now, as you guys can see, on the interval from 0 to 1, my velocity is positive. And my velocity is also positive on the interval from 2 up to 5. My velocity is negative in between 1 and 2, so negative here, negative here. My acceleration is negative from 0 up to 1.5. And then it's positive from 1.5 on up to 5. And the question that we were being asked was, when is the when is the particle slowing down? Well, it's slowing down anytime they have opposite signs. So here they have opposite signs. My velocity is positive, but my acceleration is negative. So that's the interval from 0 to 1. And there are also opposite signs right here in between 1.5 and 2, because my velocity is negative and my acceleration is positive. So those are the two regions where we could see that those functions have opposite signs. So how would we write our answer? There you go, and that's it. The particle is flowing down when the velocity and acceleration have opposite signs, and that happens on those two intervals where they were opposite. All right. Now, I told you there was another way that you guys could have done this. Instead of finding the derivative by hand, you could also find the derivative on the calculator, and I'll show you how to do that. So check this out real quick. So let's go to our y equals, and I'm going to go ahead and delete this equation. Let's say I never found the equation of my derivative by hand. Well, if you want to just graph the derivative without actually finding the derivative by hand, which probably be safer bet, honestly, because if you make a mistake while you do it by hand, you're going to get the wrong answer. You're going to push math. You're going to push 8. X goes here. You're going to put the y1 function in there, your original function. And then you're going to put in this last spot up here, you need to put an X, which is kind of weird, but you're going to put an X there. And then graph. And you'll see you actually get the same exact picture. So that way you didn't have to do it by hand. But still, you would still need to find where the blue one touches the x-axis, where the red one touches the x-axis. You would need to identify the intervals where they're each positive and negative, and then find where they're opposites. But anyway, so that's that. All right, so now we'll move on to the last bit of our study guide.
All right, guys, so for number 20 and the rest of these problems, we're going to be moving into stuff that pertains to area and volume. So the first thing we're going to do is talk about how to be finding area between two curves. So basically you have two options for this. You could do it with respect to x or with respect to y. If you're doing it with respect to x, you do the top function minus the bottom function, and you put the left x value here and the right x value here. If you're doing it with respect to y, it's the right function minus the left function, and you put the lower intersection point here and the upper intersection point here. And that's basically it. And as we talked about in class, if you're ever unsure and we're doing a calculator problem, you're welcome to go ahead and just throw some absolute value bars on there. And that'll give you a nice segue into making sure you don't have any errors. So let's go ahead and begin with our first problem here. It says, find the area of the region enclosed by the curves. They want us to set up but not evaluate the integral. So for most of these problems, it'll be like this on your test too. We're not actually going to have you punch it into the calculator and get the area. We just want to make sure that you know how to set it up right. And we still do want to graph them though, just to kind of see what the picture looks like. If they don't give you a picture, it is kind of helpful. So let's go ahead and graph these really quick and see what they look like. So we're going to type those two functions in that they gave us, and we're going to take a look at the graph, and there's the two functions. We have the blue one and the red one, and we are integrating from 0 on the x-axis to 4 on the x-axis. And so this is the shaded area that we're trying to find the area of. So that's basically what we're doing there. So how would we set up this integral? Well, we're going to do the integral from 0 to 4. Now, why is it 0 to 4? Because if we look back at our worksheet, real quick here, you'll see why. It tells us we're going from 0 to 4. Okay, so that's why we're going from 0 to 4. Now, we're going from 0 to 4, and then we have the top function minus the bottom function. So to find out which function's on top, we could just push trace, and then we could just start scrolling. And right now I'm tracing the blue line, which is the positive 2 square root of x. So that's the one that's going to be on top. And so I'm going to put that one first, minus the negative one, dx. And just so you guys know, on this test, the way that they're going to have the answers written is they're going to get rid of the parentheses and they're going to combine the double negatives into a positive. And then this is what you'll be looking for. This is the answer. Now, personally, if I was doing this, rather than letting a computer generate the questions for me, I would have just added these together and put 4 square root of x, but they're going to leave it separate like this. So this is what the answer would look like. Okay, and you guys are going to be doing a multiple choice test, so we want to make sure you guys know how to identify it. So as you guys can see, that's what it would look like. All right, let's go ahead and take a look at number 21. We're going to go ahead and graph these functions, find out which one's on top. So we're going to punch those into the calculator and graph them up, and there it is. Now, on this particular problem, we are integrating from -5 to -3. So let's see what that would look like. -5, here's -1, 2, 3. So we're stopping here at 3. And 4, 5, here's 5. So what we're doing then is we're finding some area here that starts over here. We're finding this little kind of like a triangular section, if you will, there. And then this little triangular section as well. Okay, so that's what we're finding from -5 to -3. Now, as you guys can see here, for the first half, the blue line is on top. And then for the second half, the red line is on top. Okay, so this one's going to require us to write 2 integrals. Okay, and we need to find out where this crossing point is. So we're going to do our usual process here. Second, calc, intersect, and we're going to scroll to where they cross. It's probably right at -4, but let's just make sure. Yeah, it's -4. So we have our 2 integrals then. My first integral is going to be going from -5 up to the intersection point of -4. And then my next integral is going to be starting at -4 and ending at -3. And the reason why, once again, we have to do 2 of these is because since the functions have crossed, we end up having one function on top in the first half, but in the second half, a different one. So let's see which one is which. Right now, if I were to push trace, the blue line, as you guys can see, I'm tracing the blue line. That's the x squared plus 4x minus 2. Okay, so that one would be the, I'll try to squish it in here, x squared plus 4x minus 2. And then minus, And then the red one's going to come second after that, and that's the negative x squared. I don't know if I'm going to be able to fit it in here. It's kind of tight space. Minus 6x minus 10. And for this one over here, it's going to be the reverse. The red one's going to come first. Negative x squared minus 6x minus 10 minus the blue one, which is the x squared plus 4x and minus 2. So ran out of space, but there it is. So since we're doing the setup, I could have done the setup where we do absolute value, but I just know this test doesn't write it like that. I have seen some AP questions where they, instead of setting it up like this, they'll just put absolute value on it. So that's possible. But I just know on this test that for this type of a question, they are going to want to see you split it up into two separate ones. But we're not going to actually evaluate there. We're just going to leave it at that. So that would be the answer for that one. And I'll show you what it looks like on the actual software here. So we have from -5 to -4 with the blue one minus the red one, plus from -4 to -3 with the red one minus the blue one. Okay, so that's what it'll look like. And even this software has it's so long that they split it up into two lines, but that's just how it is. So just want you guys to be prepared for what you'll see on your test. So that's what it'll look like. Let's go ahead and move on to number 22. Number 22 is asking me to find the area between the region enclosed by the curves and the y-axis. So now whenever you're trying to find a region enclosed by a curve and a y-axis, in that case, you're going to be doing an integral with respect to y. Okay, which means that your function needs to be written in terms of y instead of in terms of x. All right, so let's go ahead and graph the function first, just so we can get a feel for what this graph even looks like. I believe it was x minus 3 to the power of 3, wasn't it? I think that's what it was. No, it's x minus 4, my bad. Let's go back and change that 3 there to a 4. All right, and graph it. So that's what this function looks like. And now I want to be finding the area between this blue line and the y-axis going from y equals 4 to y equals 6. So what would that look like? Well, here's where y equals 4, and here's where y equals 6. So basically I'm finding this area right here between this curve and the y-axis. So I'm finding that area. It kind of looks almost like a rectangle, and it would have been if this side wasn't curving. So like I said, when you're finding area to the y-axis, you have to have your function, however, written in terms of y instead of in terms of x. So we already know this much. It's going to be a dy function, and we know that we're going from 4 to 6 on the y-axis. Okay, but before I can put this function over there, we got to get the x by itself so that my function is in terms of y. So first thing I'm going to do is I'm going to take the cube root on both sides. And that will cancel out the third power there. And then I'm going to add 4 over to the other side. And so we have the cube root of y plus 4 is equal to x. Notice the 4 is not underneath of the root, right? In fact, to avoid that, you might even want to just put 4 plus in the front. That way you don't accidentally write the 4 underneath the square root in this case because it doesn't belong there. But anyway, so there's that. Now, what are the two curves that we're finding the area between? Well, I'm finding the area between, let me clear this up really quick. We're finding the area between this curve and this axis, okay? Now, the y-axis is the equation x equals 0, okay? So we're finding the area between this curve, which is x equals the cube root of y and then plus 4, and this line, the y-axis, which is the equation x equals 0. So that's going to be the integral. Once again, we said we're going from 4 to 6. And we're going to have the function on the right. That would be this one. So that would be the cube root of y plus 4 minus this one, which is just 0, all with respect to y. Now, just so you guys know, once again, on this test, they're going to do some simplifying. They're not going to do as much as we would have. But just so you guys know, they're not going to have minus 0. There's no point in putting a minus 0 because when you do that, it doesn't do anything. So they'll leave that one off. But this is what the integral would look like for this one. And I do believe that on this question for the exam, they do want us to go ahead and actually calculate the area. So we can go ahead and punch this into our calculator and see what we would get. Okay, but I am going to be typing this function into my calculator. And you guys have to remember that when you do this on a calculator, you have to make your y values x values so that it actually works. So let's go ahead and type that in and see what the area comes out to be. So we're going to do math. We're going to do 9. We're going from 4 to 6. And we're doing the cube root of y. Now, I do believe there's a cube root button on this calculator. If you want to, let's see if we can find it. Math number, I don't see it here. So what I'm going to do is I'm going to just do the cube root in a different way. The cube root is the same thing as y being raised to the 1/3 power. So I'm just going to do x to the power of 1/3. That's a cube root, just so you guys know. And then plus 4. And notice I put x instead of y because, once again, our calculator prefers x. But anyway, this area would be 11.415. And I think this is going to be the only type of question on your test where I actually want you to go ahead and find the area, just so you guys know. But the rest of them are all just setup questions. So there's that. Let's go ahead and move on to our next one. So now we're going to be moving into the problems where they're talking about cross sections. For those, now we're getting away from just finding area and we're moving into finding volume now. The way that these problems work is you're going to start by finding your base. You know, what we're doing is in our base, in our area, we're going to be stacking shapes on top of this base area. And the base is going to be found by doing either the top function minus the bottom function or right minus left if we're doing a dy problem. After that, we're going to find the area of the cross section. If it's a square, it's going to be your base squared. If it's an equilateral triangle, it's the same thing, but with a radical 3/4 being multiplied by it. If it's an isosceles triangle, it's the same thing, but just with a half in front of it. If it's a rectangle, it'll be the same thing, but this number in the front will be different depending on the problem you're working with. Usually, the way that the test questions are going to be on this one is they're going to say the base, the height is half the base, or it's 2 times the base. So if it says it's half, then k will be a half. If it says it's 2 times as much, then it'll be 2. So I just put k there for some random constant that it could be. Semicircles will be the same thing with the pi over 8. So they're all the same equation, really, just different constants in the front, as you can see. So you find your base, then you find your cross-section area using one of these formulas. After that, you're ready to find the volume. And that's by taking one of these things here, A through E, and integrating it from some starting point to some ending point. And I just put D blank because it could be with respect to X or Y. You're doing it with respect to X if your cross sections are perpendicular to the x-axis, and you're doing it with respect to y if it's perpendicular to the y-axis. So let's go ahead and jump in and take a look at our first question here. So this one says the base of a solid is the region enclosed by this semicircle, which we've got a picture for that right here, and the x-axis. It says that the cross sections are perpendicular to the x-axis, so we know that we're doing a dx problem. And we're also doing equilateral triangles, so that means we're going to be doing the whole radical 3/4 times the base squared formula. So there's a lot of good information to keep in mind. So step 1 is to find the base. Okay, The base is going to be the top minus the bottom in this case because we are doing dx. And the top is, of course, just this curve up here, which is square root of 25 minus x squared. The bottom is the x-axis, which is 0. So we really don't even need to write that. So our base then is just going to be the function itself in this case. So there's my base. Step 2, the area. We've already decided that's going to be this guy. So it's radical 3 over 4, and then the base squared. Okay. Now, one way that you guys could, that x was supposed to have a square too. One way we could simplify this is by taking this 2 and canceling out that radical. I don't think they're going to do that in the software. I think they're going to leave it just like this. Now we're going to go ahead and go on to the third step, which is to turn this area piece into a volume by integrating that value. That area from our starting point to our ending point. Now, since we're doing this with respect to x, we're going from here to here, the intersection points on the left and the right side. So that's from -5 to +5. And that's going to be your final answer right there. I want to make sure that that's what it looks like. So let's take a peek here. There it is. Yep. Now notice that they put the constant out in the front. You can do that. It doesn't have to be inside the integral. That's the only difference between how I wrote it and how the test is going to be written. So we'll go ahead and do that from now on after this, just so you guys know what to look for when you're doing your multiple choice questions. But there's your basic gist of it. Let's go ahead and take a look at another one here. So it says the base of a solid is the region enclosed by this function, y equals 4, and this function, y equals x squared over 4. The cross sections this time are perpendicular to the y-axis, so we're going to be doing things with respect to y. And we're doing isosceles right triangles where one of the legs is in the x and y plane. And I mentioned to you guys in that case it's going to be 1/2 times the base squared. Okay? Let's go ahead and begin here. So step 1 is to find the base. Okay, the base, since we're doing this with respect to y, it's going to be the right minus the left. And so in that case, we need to find this area, that segment minus this segment. So the base is the distance between those two functions there. So that curve is this one right here. That's y equals x squared plus 4. Since we're doing this with respect to y, we need to get this thing solved for x. So we need to get the x by itself. So let's do that. The first thing we would do on this is we would multiply both sides by the denominator, like that. So I've got 4y equals x squared. And then we would take the square root. And when you square root, you get a plus and a minus. And as we've mentioned before, the positive one is the right side of the curve. So I'll highlight that with pink. And then the negative one is the left side of the curve. So in this case then, right is radical, wrong writing utensil, is radical 4y minus a negative radical 4y. And I do believe they're going to go ahead and just combine those into a positive. Now, whenever I was doing these types of problems, I put it together like this. But I'm pretty sure on this test, they're just going to leave it like that, just so you guys know. So we'll just stop there while we're ahead. Step 2, we want to do our area. And as you know, since we're doing isosceles right triangles, we're going to go with that formula. So it's 1/2 times the base, which we found in step 1 already, squared. And then step 3 is to turn that area into a volume by integration. So we're going to put the constant in the front from now on, we said. And then it's square root of 4y plus the square root of 4y squared dy. And what do we integrate to and from? Well, when you're doing it with respect to y, you go from the bottom point up here to the top. So that is going to be from 0 to 4. And so that's what that particular answer would look like. Let's go ahead and move on to another question here. Now we're going to move on to a new type of question here, another volume question, but a different kind of volume question. There are 3 types of volume questions. We just finished the last one, which was cross sections. Then we have this one, which is the disk method. The third one is the washer method. So let's go ahead and take a look at the steps for the disk method really quick. So when you're trying to find the volume of solid generated by rotation using the disk method, first of all, how do you know when you're doing the disk method? That's when there's no gap between the area that they give you and the axis you're rotating that area around. What do I mean by that? Well, here's my area. That's this little shaded blue region. And here's the axis. Do you guys see how the axis is right on? It's a part of the area there. If your axis was down here, if it was separated from the area, that would be a washer method where you get a hole when you rotate it. But when the axis is right on the area like that, that's going to be a disk method. And so that's what we're going to be looking at in this particular type of problem here. So first thing you're going to do is you're going to find your radius, which is the function minus the axis. Now I put that in absolute value bars, but you guys do need to understand that on this exam, they're not going to be using absolute value bars. It's function minus axis, or it could be axis minus function. It depends on which one's on top. If the axis is above the area, then it's going to be axis minus function. If the axis is below the area, like the question we're on right now, the axis is underneath of the area, then you're going to do the function minus the axis. Okay, so after you find your radius, the area that's generated as you rotate one section around is a circle, so it's pi r squared, where the radius here is what we found in step 1. And then to turn that into a volume, you would integrate that area that you found in step 2. So whatever you got here in step 2 just gets plugged in down here. Now, notice I put a blank here because it could be with respect to x or it could be with respect to y. It just depends on what your axis is. If you have a horizontal axis of rotation, in other words, a line that goes like this, then you're doing a dx problem. If you have a vertical axis of rotation, one that goes this way, then you're going to be integrating with respect to y. So let's go ahead and jump in on our first example here real quick. All right. So notice that my axis is y equals 2, and you can tell from the picture here that that is a horizontal line, and that tells me we're going to be doing a dx type of problem here. Another thing to notice here is that the function or the area is above the axis. So for my step 1, it's going to be function minus axis. Okay, and so the function here is x squared plus 2. That's the blue curve there. And the axis is the line 2. So there's my radius. I'll just call it big R there. Okay. Now step 2 is we want to find the area. So to find the area, it's pi r squared. And my r in this case is going to be this. Now, I do believe they're going to simplify these a little bit, like they'll combine these constants together. And so you're going to just end up with x squared because the positive 2 and negative 2 cancel out. Step 3, we're ready to find our volume. The pi is a constant, so we're going to put that in the front. We're going to have x squared squared there. And what are we integrating to and from? Well, since we're doing this with respect to x, it's going to be the left point to the right point. So that's from 0 to 2. And that would give us the volume of this blue area being rotated around that particular axis. Just to make sure, let's go ahead and check to see how they wrote their answer here with the software to make sure it matches what we have. And it does. That's what we have. So on these types of problems, I'm noticing they just combine the constants. You know, we had plus 2, minus 2, and they put them together and canceled it out. Why they chose to do that here, I don't know, but that's just how they do it. So be ready for that on your exam. Let's go ahead and take a look at another one. It's another disk method. All right, I just changed 26, but this matches what's on your guys' worksheet here. I wanted to do one that had a vertical axis of rotation, so that's what we got here. You guys can tell from the arrow here, the axis is a vertical line. So whenever you have that kind of a situation, you're going to be doing a dy type of problem. And when you have a dy type of problem, you need your equations to be in terms of y instead of in terms of x. In other words, we need to get the x by itself, so the rest of the equation has y's in it. So let's begin by doing that first. First of all, I want to get rid of that square root. I'm going to do that by squaring both sides. And then I'm going to minus the 3 on both sides. And I don't like that negative there with the x, so I'm just going to divide everything by a negative 1. And that ends up giving me negative y squared plus 3. And that's good enough, but I'm pretty sure in the software how they're going to write it is they're going to put the negative 1 second, so they're going to write it like this, positive 3 minus y squared. Okay, so we're going to change the equation into that before we even begin. So I'm just going to put an x through that, and I'm just going to put here 3 minus y squared, because we already know that's the one we're going to use since we're doing dy, because we have a vertical axis of rotation. All right, so let's begin here. Step 1 is to find our radius, and our radius is going to be either function minus axis or axis minus function. So here's the function, and then here's the axis. Now, since we're doing this with respect to y, it's right minus left. So which one is on the right? Is it the function or is it the axis? You guys can see this one is to the right of the pink, right? So that's the function. So once again, it's going to be function minus axis on this problem. But remember, it can be axis minus function if the axis were to the right of the function instead. So we have our function, which is 3 minus y squared, minus our axis, which is right there. That's the line x equals negative 1. And we are going to go ahead and simplify this. So first of all, that's a plus because you have double negatives. And then the 1 can go with the 3 to make 4. So it's going to end up being 4 minus y squared is my radius. Step 2, the area is pi r squared. And my radius, as we've already said, is 4 minus y squared. And then step 3, the integral, pi on the outside, is our area being squared. And we're integrating with respect to y, which means that we're going to be going from top to bottom. Okay, so the lowest point down here is 0. And where we stop is here. That's the highest point. So we're stopping at 2. Okay, and so that would be that particular problem. Once again, let's just check to make sure we got our integral looking right. I thought they would have put the y squared after the 4 and had 4 minus y squared, but it doesn't matter, I guess. Either way, we were pretty close. Same thing, just different way of writing it. All right, let's go ahead and move on to number 27. Now, on number 27, there is something different that's happening here. Here's my area. Here's my axis. Do you guys see what's different? This time, there's a gap between them. And when there's a gap, we're now dealing with the washer method. So let's go ahead and take a look at the steps for the washer method. So the washer method is what you use when there's a gap between your area and the axis of rotation. When you have that, really what you're doing is you're rotating 2 functions around an axis, and as a result, you get 2 radiuses, a big radius and a little radius. The big radius can be found by subtracting the function that's farthest away from the axis and the axis itself. And the little radius can be found by subtracting the function closest to the axis from the axis itself. And once again, axis could come first and then the function, or vice versa. It just depends on which one is on the top or bottom or left or right if you're doing it with respect to y or x. So for these guys, the area is pi times the big radius squared minus the little radius squared, and that whole thing there gets plugged down into here to integrate so that you get the volume. And the same principle applies here as it did on the last set. A horizontal axis of rotation is a dx, a vertical axis of rotation is a dy. So let's go ahead and jump in and get started on our first washer method problem. All right, so notice I've got a vertical axis of rotation, so we are doing a dy, which is cool because my equation's already set up like that. So I don't have to get any variables by itself. So let's go ahead and do step one, which is the big radius. So I've got two functions here. Let's take note of that. We have this function, y squared plus x. I'll highlight that in red. And then we also have this function here, x equals 2. That's the green one. And then we have our axis over here, which I'll highlight in brown. So there's my axis. Now, question for you. Which one of the functions is farthest away from the brown line? Is the green line farthest away, or is the red line farthest away? Well, it looks like the red line is farthest away, right? So the red line is this guy here. So now, should it be axis minus function, or should it be function minus axis? Which one should it be? Well, notice that the function is on the right and the axis is on the left. And when you're doing things with respect to y, it's right minus left. So in this case, it's going to be function minus axis. So my function is negative y squared plus 6 minus the axis, which is at x equals 0 apparently. And we don't really need to include the 0. So my big radius is simply the function itself. Okay. Step 2 is to find your little radius. And so that's going to be the green line minus the axis. Okay. And once again, the function is to the right of the axis, and therefore it's going to be the green line, which is x equals 2, minus the axis, which is 0. 2 minus 0 is just 2. And so there is my little radius. So I've got my big radius, the red line, the red equation here, negative y squared plus 6, and my little radius, 2. All right. Now we're ready for the next step. The next step is to do the area. The area is pi times the big radius squared minus the little radius squared. The big radius, as we said, was negative y squared plus 6, and the little radius was 2. All right. And then for final step there, on step 3, we're going to do pi integral of the rest of this stuff here. So negative y squared plus 6 minus 2 squared, and all that's with respect to y. Now, it seems pretty simple to me just to square that 2, but I don't think they're going to do it. Let me see. How do they write their answer? I didn't quite finish, by the way, because I didn't include the limits. Yeah, they don't square the 2. But anyway, notice the limits are from negative 2 to positive 2. I didn't write that, so let's go back and put my answer up. What are the limits? Well, we know they're negative 2 to 2 because we can see the answer there. But why is it negative 2 to 2? Well, when you're doing with respect to y, you go from the lowest point to the highest point vertically. So that's from negative 2 to positive 2. All right, let's go ahead and move on to our last one. I believe it's our last one. Yes, it is. Okay. So on this one, we are doing a horizontal axis, and that means we're doing a dx. I'm going to change this up a little bit, just a second. All right. I changed it because I didn't want to have another axis that was right on the x-axis or y-axis or something. Anyway, you guys have the right one on your worksheet, so it's okay. Let's go ahead and take a look at this one. Notice that I've got a horizontal axis, so that's a dx problem. And when you have a dx problem, your functions need to be in terms of x, which is kind of interesting because they're not right now. That is not a dx problem there, so we need to fix that. So let's begin the problem by fixing that to begin with. So I need to get the y by itself, so my problem is in terms of x. So the first thing I'm going to do is I'm going to square root both sides. Now, when you square root, though, remember, you always get a plus and a minus. And then we're going to go ahead and add 2 on both sides. All right, there's that. Now, whenever you are doing a dx problem and you get a plus and a minus like that, the top one represents, the positive one represents the top half of the function, and then the negative one represents the bottom half. Now, as you can see, the area that we're working with is only the top half, so we don't really care about the negative part of this answer. And so my function that we're going to be working with is simply positive square root of x plus 2. Okay, so that being done, let's go ahead and move on to the rest of the problem. So we're not going to use that. We're going to say y is equal to the square root of x plus 2 instead. All right. So we have, I'll highlight that in red. That's this line right here. And then we have the bottom half, which is this line here, right? And then we have our axis of rotation, which is way down here. Okay, so let's begin. Step 1 is to find your big radius. I'll just put capital R. And it's going to be top minus bottom, or now which one of these functions, the red one or the green one, is farthest away from the brown line? Well, it's the red one. So it's going to be the function minus the axis. In this case, my axis is -2. And so that becomes a positive, and they're probably going to add those 2's together to give us 4. So that would be my big radius. Let's go ahead and find our little radius. That would now be the distance of the green line from the brown axis. So the green line there is y equals 2. So we have function minus the axis, which once again, we can just add those together and give 4. So we have our big radius is the square root of x plus 4, and we have our little radius, which is just 4. Now we're ready for step 3, which is the area. Pi, big radius, squared, minus little radius, squared. And then finally, step 4, we can turn that into a volume that's created by rotation, where we put the constant on the outside and we do the rest of it on the inside. So big radius minus little radius, and that's dx. Now, since we're integrating with respect to x, we go from left to right to find our limits. So my left intersection point here is at 0, and we're stopping here at x equals 1. So it would be going from 0 to 1. All right, and I'm pretty sure that's how the answer will look there, but let's go ahead and just check to make sure that that's what it should look like. Yeah, there it is. All right, guys, so that's it. Area, volume, and stuff for the last half there. But anyway, we'll see you guys in class. Good luck on your last unit test of the year.